Let's begin. Good afternoon, everyone, and welcome to the Dick Thomas Memorial Student Competition for 2020. We want to thank all of the students and their advisors and our judges and all the volunteers who have helped make this digital competition possible in the absence of the conference. We appreciate all of the flexibility and patience that you guys showed from the judges and students as well. We hope this year's competition will provide you with valuable experience for your future work. Before we get started, I just want to go over a little competition etiquette. Students, please keep your cameras and microphones off until it is time for you to present. Judges, coordinators, conference volunteers, etc., could you please keep your cameras on and your microphones off so that you can serve as the audience until it is time to ask questions. And at that point, if you do want to ask questions during the 5 minutes after the presentation, you are free to do so. It might be best to do the raise hand method in the chat, unless we can, maybe we'll be able to just ask questions without talking over each other. So, and to everyone who's in the chat, please silence your phones. And if we have any extra guests, please keep your microphones and cameras off during the presentations. Okay, so for a little historical background on the competition, the Richard Dick Thomas Award was established to honor the Washington State GIS pioneer and mentor, Dick Thomas, who passed away in 2006. The intent of this award is to honor Dick Thomas by continuing his work of encouraging students to present their original research in GIS, geography, or a related discipline at the annual RUSLE conference, and to help students transition successfully into careers related to GIS. So we express a big thank you to Dick Thomas and the legacy he has left for our students. Next, we're going to introduce our judges and coordinators. And so when I introduce you, could you unmute your microphone and say hello so that your video pops up on screen temporarily? We're going to start with Christina Shelf.
Hi, everyone.
Hope that worked for everyone. She is the GIS supervisor for City of Tacoma, and she was the winner of the 2017 Master's Level DTA Award. And she was the faculty mentor of the 2018 group winners. Our next judge is Brandy Ritchie. I might have mispronounced that already, even though you already told me.
No, you got it perfect.
Thanks, Brandy. She is the Spatial Services Manager for Pierce County, Washington. Our next judge is Dane Carson.
Hello.
Hey, Dane. Dane is a GIS analyst for the City of Auburn. Thanks for joining us. And our last judge is Heather Glock, who is a local government account manager for Esri.
Hi, everyone.
Hey, Heather. We might have Steve Beinborn joining, who is our WAURUSA board president and manager of departmental GIS at the City of Seattle. We also have Kirsty Burt here, our 2020 WAURUSA conference coordinator.
Hi, everybody. Nice to see you. Looking forward to your presentations. Thanks for having me.
Thanks, Kirsty. She's also a GIS consultant in Seattle who does work for nonprofits, school districts, and local government. So we also have Anna Yost. Anna's here, yes.
Hi.
Hey, Anna. So Anna served this year as a coordinator mentor for us on the project, and she is a previous coordinator and also a previous winner for her 2014 presentation on elk habitat modeling in the North Cascades. And currently she is a GIS project coordinator for the City of SeaTac. And then last, we have our two Dick Thomas Award coordinators, Dan Miller, who you all know Dan. He is an E911 GIS coordinator for the State of Washington 911 office, and one of this year's Dick Thomas Award co-coordinators. And I am the other co-coordinator Taylor Dixon, and I'm a senior GIS analyst for Seattle Public Utilities. I think I also missed that Maria Sevier is here, and she was also an advisor. Thank you, Maria, sorry. She was also an advisor to the conference this year as well. And I don't have what you actually do, so feel free to chime in, Maria.
I'm a GIS professional, and I own my own business. It's called Northwest GIS Consulting.
Thank you, Maria. Okay, we might have a few other volunteers in the audience, and we will definitely recognize them at the end. But we wanted to get the people who helped coordinate it at the start introduced. So for a quick reminder on the rules, each group will have 15 minutes to present with up to 5 additional minutes for questioning and scoring. During the questioning, the next group should be preparing to present. Anna Yost will be messaging you time indicators via your chat bars. So keep your chat bars open and keep an eye on the time. And before we start our first presentation, I want to give a little bit of warm advice to our students. And that is, as you present, remember to breathe and keep in mind that many of the volunteers and judges here have been in your shoes in the years past, and we are all enthusiastically wishing you best as you present. So now it is time for our first presentation. The order was determined by the order that the abstracts were submitted. So our first presentation will be given by Michael Sowa, Rhys Coffey, and Marco Evert from the University of Washington GIS CERT program. And they will be presenting their project on evaluating the magnitude of floodplain loss and identifying restoration potential in the upper Columbia River Basin. The 3 of you can turn on your cameras, and one of you can share your screen and unmute your microphones, and we will give the floor over to you.
Awesome, thanks, Taylor. Let me share my screen real quick. All right, so thanks for that introduction. I guess we can just get started here. So just to give a little background on our project, we're looking at floodplains, and these represent really vital and complex ecosystems that are essential habitat for a large number of species, especially spring Chinook salmon, which is currently listed as endangered, and steelhead, which is currently listed as threatened, and a number of anthropogenic disturbances in the upper Columbia River watershed contribute to what's called vertical stream incision, which ultimately results in a loss of floodplain connectivity. So our project sponsor, the Upper Columbia Salmon Recovery Board, tasked our student group with utilizing GIS to create a framework for watershed scale evaluation of stage 0 floodplain restoration potential in this basin. And this would otherwise be conducted by time and resource heavy individual field investigations. So we wanted to see if there was a way to do this on a much larger scale with less resources that needed to be allocated. So what is vertical stream incision? This is a process in which the stream cuts downward into sediment or bedrock, and this is often the result of changes in runoff characteristics or sediment load. And stage 0 restoration aims to restore historic floodplains by raising the channel bed, ultimately by filling in the incised channel and regrading valley floors. And it really allows a lot of complexity to return and creates a lot of really good habitat, specifically wetland habitat for essential species.
Right, so we had 3 primary goals over the course of this project. The first one was to focus on site suitability. We wanted to highlight areas where stream incision was likely to occur and accordingly result in loss of floodplain connectivity. The second goal was to look at causality and gain a better understanding of certain factors that result in stream incision within our study area. And our final goal for this project was to analyze the number of identified sites to ultimately determine the extent of stream incision, to understand if they'd be good candidates for the stage 0 restoration approach. And then this is our study area. We focused on these 4 watersheds here.
All right, so I'm going to start out with the methodology, and we broke our project up into 3 phases, and the first was a site suitability model. So because we're looking at 4 very large watersheds that represent a large portion of this upper Columbia River Basin, totaling over 5,000 square miles, we knew we would need a way to narrow down sites for further evaluation. So in forming the requirements for this model, we considered 3 questions. The first being, where are there current or historic floodplain zones? And by doing so, we looked at valley confinement. You know, is it a narrow canyon or is it a broad valley where we would expect to see maybe an adjacent floodplain? Slope, and then soil type, are there alluvial soils? Our second question we considered is, where would we expect to see a loss of floodplain connectivity? And this is a little bit harder question to answer, but with the help of our sponsor, we learned that a good indicator of a loss of floodplain connectivity is coniferous forest encroachment on what used to be riparian zone. So what we did is we took land fire inputs here and we used their biophysical settings file as well, which is an estimation of pre-European settlement conditions, as well as their most recent land cover file. And we looked at changes between those two, and specifically changes from riparian to some of these other coniferous forest and coniferous hardwood type environments. So we can see in this little screenshot here, these red cells represent, this is part of the Entiat River, and these red cells here represent changes from riparian to coniferous forest, which is a good indication that this is a site we want to do further evaluation on. And then our third question we considered is, what are the appropriate stream types for this restoration? And we ultimately used stream order for this using the Strahler method. Anything that was up in the higher stream orders is really not suitable for this type of restoration. You can't really fill in an incised channel for a very large river, so we needed to limit it in some way. So in addressing questions 1 and 2, we used a weighted overlay portion of our suitability model. We weighted the land fire vegetation departure very highly because this is our only indication of where floodplains could have been lost. And we also weighted the USDA's valley confinement algorithm results pretty highly because we can say almost certainly that there will be no floodplains in a confined valley. And then finally, the search was limited to 1st through 4th order streams, as these are the most appropriate for stage 0 restoration as defined by our sponsor. And we applied a 100-meter buffer to these, which was then used to clip the resulting shapefile to ensure that the results were limited to the correct stream types. And in doing so, we built a model using ArcPro's model builder with all of this analysis to ensure that it could be, 1, well documented, and 2, easily reproduced, either for other weightings within the weighted overlay, if we wanted to include other characteristics, or if we wanted to run this in different areas. And then our final step, we learned from experts at the US Forest Service that we really need to be looking for valley type. And unfortunately, there isn't a great way to quantify valley type. So what we did here, we were looking for what's called a response valley, which in this diagram on the left is represented by the depositional zone. So we took our results of our suitability model and we created a triangulated irregular network, brought this into ArcScene, overlaid some aerial imagery, as well as the results of the suitability model. So we looked for, dark red regions, as you can see in this image on the right, as well as that appropriate valley type. All right, so that brings us into our second phase of our analysis, which was our causal influence evaluation. And we identified 3 causes that we wanted to look at, one being fire history, the second being logging operations, and the third being built roads. And it should be noted that these 3 disturbances in the region date back to the late 19th century, and we don't have data available for that. So legacy stream incision causality cannot be accurately quantified, at least at this time. So these results should be interpreted as the current relative influence of these 3 factors on vertical stream incision. And the data sources for these were the Washington large fires from 1994 to 2018, logging from the Forest Practices application from 1995 to 2020, and then the files for both roads and then orphaned and abandoned roads in the region. And so the way we did this, we prepared these inputs we buffered the roads to create a polygon, and we merged all of these polygons together in order to create this raster file that we then reclassified. So we characterized everything having one of these three causal factors with a score of 1, and everything that did not have these causal factors with a flow of 0. And with that, we used 10-meter DEMs with the flow direction and flow accumulation tools using multi-flow direction. And we used our weighted raster in 1, and then we ran the flow accumulation again without a weighted raster. So when you run the flow accumulation without a weight, it assumes that all cells get a scoring of 1. So then we use this to define what we're calling, for the purpose of our project, the stream incision causal index, which is just an indication of the total upstream area containing at least one of our 3 identified causes relative to the total upstream area. And this ranges from 0 to 1.
All right, so now I'm going to discuss what was basically the final method of geoprocessing for this project, which is the creation of relative elevation models for sites that have been located by our suitability analysis. So what is a relative elevation model? How does it differ from the more common digital elevation model? And why is it important for determining how to proceed with the restoration process? A digital elevation model incorporates elevation data such as LiDAR to highlight topographical changes across a given geographic area. And this is shown in the left image, and you'll notice that one shortfall of this analysis is that stream features within the imagery are not easily discernible. And this is, of course, because streams always span from higher to lower elevation. The relative elevation model, on the other hand, that's shown on the right, is different because it takes the stream's change in elevation into account and controls for it once the valley slope is identified. Relative elevation models are more useful for this type of restoration practice because they give us a clearer understanding of stream features and therefore better inform the degree of incision that has occurred. And this will ultimately determine if the site is a good candidate for stage 0 restoration. So I'll walk you through a bit of our process of creating relative elevation models. We used an external plugin to ArcMap for our creation of relative elevation models called the Geographic Gradeline tool. So this tool is composed of a series of functions that build on one another to take a digital elevation raster input and convert it into an REM. The first step in running the Geomorphic Gradeline tool is to highlight the valley centerline, and this centerline's elevation ultimately dictates how the surrounding elevations are normalized. And as you can see in the top left image, we've used the suitability model that Michael had previously discussed to determine such appropriate locations for running the tool. So it's important here to specify exactly how much on either side of the centerline you want to include in your model. And really, it's just best to ensure that your analysis extends sufficiently into the adjacent hillside so that you can safely capture the valley floor. In image 2 here, we've now created cross sections extending perpendicularly from the centerline at 1 meter intervals. And we also show a graph that represents elevation along the extent of a particular cross section. It's helpful to imagine each one of these cross sections ultimately being raised or lowered, so to speak, relative to the elevation of the center line. And then in the third step, we want to create a trend line of the center line elevation that essentially captures its slope. The trend line is created in some part by playing around with different order polynomial functions to ensure that it fits the slope appropriately. And again, this trend line input representing slope is really important because it essentially serves to normalize the elevations of its cross sections. Later, we can ultimately see the valley's newly adjusted cross sections as they exist above and below that value. And finally, now that we've adjusted our relative elevations, we're able to symbolize them accordingly with our newly created relative elevation model.
Okay, next we're going to look at the suitability model results. We use these suitability model results to identify sites to run the Geomorphic Grade tool on. So first we have the Wenatchee Watershed, where we evaluated a total of about 250,000 acres. Of 6% of that area are considered to have high to very high level of suitability. And as you can see here in the map, we have a widespread suitability in the Wenatchee Watershed. Next, we have the Etiquette Watershed. We evaluated a total of 47,000 acres. 7% of that area are considered to have high to very high level of suitability. And as you can see in the figure on the right, the main stem of the Etiquette River is high priority. It's just that very red line running down the middle. Next, we have the Methow watershed. We evaluated a total of 290,000 acres, and of that 5% of that area are considered to have high to very high level of suitability. And we kind of see the suitability in the upper region of the Methow watershed here. Then we have the Okanagan watershed. We evaluated a total of about 337,000 acres. 8% of the total area considered is high to very high suitability. Again, we have widespread suitability across the watershed.
All right, and then this is just an analysis this is just showing the footprint of the causal factors we considered. This is fires, logging, and roads. And you can see that it corresponds very closely at this scale with the Incision causal index. However, when we're able to zoom into a little closer scale, you can see the impact of the upstream effects. You can see you can see the upstream impacts of this. And this is something that we ultimately used on kind of a site-by-site basis. That's why we wanted to define that causal index, because it's something we can take as a good indicator for each of our sites that we'll outline next.
So we evaluated 21 sites in total across all 4 watersheds, encompassing over 5,970 acres. We're going to show you 3 today. First one is 8 Mile Creek. It is located in the upper Methow Basin. We evaluated a total area of 65 acres. The minimum elevation was negative 7.62 meters, and the incision causal index was 0.61. And the yellow circle represents an area of the creek that may be a potential restoration site based on the REM results. Next, we have the Mad River, located in the Etiquette Basin. We evaluated a total area of 68 acres in this segment of the Mad River, and the minimum elevation is negative 10.41, and the incision causal index is 0.009. Lastly, we have Chilliwass Creek with 289 acres evaluated. It has a minimum elevation of negative 4.6 meters and an incision causal index of 0.818, which is a much larger value than our other 2 sites, which shows that there isn't necessarily a correlation between the incision causal index and the minimum REM elevation based on our observations. So the next step, we're going to hand off all 21 evaluated sites to river restoration experts to decide where stage 0 restoration would be most beneficial.
And ultimately, our hope for this project is for it to serve as a framework for future watershed scale stream restoration efforts, potentially with other factors considered. And we think there's just kind of a lot to build off of here. And with that, we can open it up for questions.
Thank you. Judges, can you unmute your mics and feel free to chime in with questions?
Hi, I'll go. So you've identified huge acres of land that have, what is it, like very low to very high priority of restoration. I was wondering, does like stream connectivity or connecting different parts of the watershed play into it, or is it more about creating habitat and kind of more of that sort of wetland habitat?
Ideally, it's most involving just creation of more habitat. I think, connectivity is important because if there is, connected habitat, that is essentially better for larger runs of fish. But I think that just having any wetland habitat is helpful for these essential species in the area.
I have a question. What did you find to be the most challenging aspect of this project technically from a GIS perspective?
I can, maybe we can touch on this more too, but one limitation that we had was lack of data. So, all of our data is essentially derived from LiDAR, and we only had one source from that, which was the DNR portal. And with that, it was quite spotty in many areas. And so it took a lot of effort to mosaic that together. And that also affected the scope of our project in terms of what sites we were actually able to. So that was a main challenge, I'd say, at least one.
Do we have
I
any
have a
other
question
questions?
for you. I have one. So everything you did was over on the east side of the mountains. Is this applicable over on the west side? Are we going to see similar indexes being used on this side of the mountains? Something we can bring into our LiDAR data and use?
I think we certainly could. Yeah, absolutely. This was concentrated on the east side mostly because our sponsor is out in Wenatchee, and these are kind of local watersheds for what they were looking at. But I think that this could very easily be reproduced in King County or on the western side of the state. Absolutely.
Good. We just got new LiDAR collected. I'd be interested in trying to do something like this with it.
Oh, excellent.
Thanks. Good job too.
Thanks.
All right. If we don't have any more questions, thank you to Marco and Rhys and Michael. And next we are going to have Amanda.
Oh, I think you just muted yourself. I see you talking.
Sorry about that. I apologize.
It's okay.
Next we have Amanda Moody from Central Washington University, and she will be presenting her project, which is comparing revised universal soil loss equation calculation methods across varying DEM resolutions. And Amanda, keep an eye on the chat because I will be giving you time indicators.
Alrighty. Okay, so getting started, as he said, comparing RUSLE L calculation methods across varying DEM resolutions. So my work is on specifically the L factor of the revised universal soil loss equation, or RUSLE. Now this model estimates long-term soil erosion by water from rill and inter-rill erosion. Simply put, this model consists of 6 factors, each quantifying an effect on erosion rates, multiplied together as RKLSCP. The units for these is derived from the units selected for K and the time period selected for R. L, S, C, and P, however, are dimensionless ratios. And this is a ratio to the erosion of a reference plot that has a 9% slope, length of 72.6 feet, and maintained in a continuous tilled fallow condition with straight row farming. Now, originally this model was used on smaller sites and farm fields and other similar areas where 1 to maybe a few values could be used to represent each factor. But with the rise of GIS, this model has been increasingly applied to a wide range of sites and conditions. So the L factor is one of the hardest of the factors to define and calculate, and it is relating to the influence of slope length on erosion. Traditionally, estimates of slope length were estimated from in-the-field measurements where labor, time, and money would restrict the number of samples used to represent an entire area. For this reason, GIS is able to offer that platform to predictably and reliably repeat slope length calculations that removes errors caused by those personal judgment calls of trying to define what a site's slope length actually is. For my project, I compared L factor outputs using the grid accumulation method with and without the incorporation of a slope cutoff variable, and then the accumulating area method using a multiple and a single flow direction algorithm. These outputs were then compared across varying DEM resolutions of 1, 5, 10, and 30 meters. Since there was no already pre-built tool to calculate the slope length I needed, I did create a Python program to be able to calculate the L factor. using the grid accumulation method and calculating slope lengths. So the L factor equation requires two input variables, slope length and angle shown on the slide as lambda and theta respectively. Slope length is officially defined as the horizontal distance, so imagine how the bird flies, from the point of origin of overland flow to the point where either the slope gradient decreases enough that deposition begins, or where runoff becomes concentrated in a defined channel. So the site I will be using for this presentation is in Okanogan County in north central Washington. This area is a largely open arid rangeland with ponderosa pine dominated forests and woodlands. Precipitation occurs predominantly in winter and spring as rain and snow melt. This site in particular burned in 2015 and was then effectively reseeded by DNR the following fall. However, the main access, or the only access road, was washed out soon after that. Besides this large erosion event that is fairly typical for the area following large fires, the more average long-term erosion patterns appear to be on exposed outcroppings or disturbed vegetation as interreal erosion. There are still multiple old dirt roads, mostly unused since that access has been washed out, which have transected slopes and have now allowed for a greater establishment of like grasses and herbs that are protecting the soil from erosion. So my first method, the grid accumulation method, adds slope length starting from the high points in the map following flow direction, which is that steepest downhill path, to a defined drainage channel or the outlet of the basin. Slope length is first calculated for each individual cell, depending on flow direction and the cell resolution, and then these lengths are added following that flow direction pathway. Where two flow paths meet, the longest length takes precedence and continues while the other is terminated. Finally, that accumulating slope length value through the cells is used to calculate the L factor for each cell. As I mentioned previously, this method is also incorporating a slope cutoff variable, which represents areas where deposition occurs. It is a user input value between 0 and 1 that represents a % change in slope to the receiving cell. A value of 0 means that any change in slope will reset that slope length, and a value of 1 means that the slope length will never reset. Now, ideally, these would be set by an expert at the study site. Otherwise, a recommended value of 0.5 can be used. And what that means is that a slope change of at least 50% is needed to reset slope length. So the grid accumulation method without slope cutoff produces greater maximum values and so longer slope lengths. Here are the raster outputs using a slope cutoff of 0.5 on the left and using a slope cutoff of 1 on the right. The darker the shades, the lower the L values. This 5-meter resolution is able to visually highlight patterns in specific areas within the study site that have the highest erosion related to slope length, while maintaining some of those smaller scale features that interrupt flow like roads. And here is a difference raster. The darker green lines are the paths that have greater L values when slope length is not reset. So when using 1 for that slope cutoff variable. The upper right of this basin shows a fairly dramatic difference when you are using the slope cutoff variable. The area that I circled in black is where an old dirt road resides, about 8 feet wide. And this is transecting the slope. You can see that without using slope cutoff, the flow paths continue all the way down into the drainage channel with larger L values, not accounting for that intersection with this old road and its influence on water flowing down the slope. So for most landscapes, the incorporation of the slope cutoff variable at 1-meter resolutions, shown on the left, allows to account for fine scale variability. Sudden changes in steepness that occur from barriers or microfeatures that interrupt flow and break that slope length are detected. However, visually interpreting these erosion estimates at this resolution is noisy, kind of like an old TV static, and it can be difficult to identify patterns or even locate problem areas. Resolutions coarser than 5 meters, however, such as the 30-meter resolution on the right, smooths the landscape by representing those large 30 by 30 meter areas with a single value. This loses important features such as roads and produces less meaningful results of erosion in the landscape. So the next method, the contributing area method, substitutes area for slope length. And the argument for this is that overland flow doesn't depend on that distance of flow from a point of origin, but rather on flow convergence and divergence over the area per unit contour length, so cell size, contributing flow to a specific point. And while this method can account for these, it can't account for areas of deposition. And so also in order to substitute area, there is a different equation used to calculate the L factor shown on the screen. The contributing area, A, in the equation can be calculated based off of a single or multiple flow routing algorithms. And these algorithms dictate how much flow from a cell is directed to which downslope neighbors. Here is the contributing area method at a 5-meter resolution using a single flow direction algorithm on the left, and on the right is using a multiple flow direction algorithm. The lighter the color, the higher the L value. The contributing area method overall is sensitive to where flow begins to concentrate near those defined channels and starts producing exceptionally high L values as almost all upslope areas being combined. The single flow direction algorithm has high L values quickly concentrated in more easily identifiable patterns, while the multiple flow direction algorithm disperses area in like a fan before starting to braid and converge towards those defined channels. So here's another difference raster where the multiple flow direction algorithm is producing higher L values shown by the tan and brown colors. The multiple flow direction algorithm splits and distributes area to more downslope neighbors, so there are more cells with slightly overall higher L values. Most of the smaller differences between the two algorithms appear to occur in open slopes where topography does not naturally aggregate flow into drainage channels. So the multiple flow direction algorithm has more neighbors to split flow to. The larger differences that are occurring closer to those defined channels are where more areas being concentrated by the multiple flow direction algorithm than the single flow direction algorithm is able to pick up and do. So now finally on to the differences between these two L factor calculation methods. Here is a difference raster of the grid accumulation method without slope cutoff subtracted from the contributing area method with a single flow direction algorithm. Differences between the methods grow larger as flow becomes concentrated moving downslope, especially along drainage channels. This is corresponding to how each method treats convergence in the landscape. The contributing area method combines accumulated area where two or more paths converge, allowing for all area in the site to influence values downslope. The grid accumulation method only continues the longest flow path. The flow paths that are ended no longer influence values downslope. Now, this treatment of convergence and no equivalent of a slope cutoff variable becomes increasingly important in large catchments or catchments with large elevation change. The contributing area method will increasingly produce higher and higher values in these conditions with greater available area to distribute that could lead to an overprediction of erosion in more areas of the landscape. So to determine the statistical significance of the differences between these method outputs, I conducted a two-sided hypothesis test with a null hypothesis that two independent methods at the same resolution were drawn from the same distribution. The site that's been displayed for this presentation is site D, which is at the very bottom of the slide. The grid accumulation methods were statistically different from the contributing area methods at the 1% significance level for all resolutions for each site. The contributing area method using single flow direction algorithm is also statistically different to the multiple flow direction algorithm at all resolutions, again at each site. However, the grid accumulation method using slope cutoff remains statistically significant to not using slope cutoff for all sites at a 1 meter resolution. However, as the resolution becomes coarser, the occurrence of statistical significance decreases. This, in combination with the loss of fine scale features at 10 and 30 meter resolutions, tells us that the differences between using these methods are lost to landscape smoothing as cell size increases. So soil erosion models such as the RUSLE aid land managers and policymakers in the use, management, and conservation of soil resources. Recent economic models using RUSLE have estimated that the cost of soil erosion to the US as $44 billion a year. Understanding the differences in method choices when producing RUSLE estimates helps to discern the validity and confidence in the estimates provided. Differences between using the grid accumulation and the contributing area method grow as the size of the study area enlarges, greater elevation change occurs, and the landscape complexity increases. For those large and complex sites especially, the grid accumulation method is advised since the contributing area method will produce very high L factor values. Also, more is not always better. A very fine resolution does not necessarily always produce the best outputs. A resolution of 5 meters is recommended for most uses since it is still able to detect those fine scale features that alter flow in the landscape. But this resolution allows for a more meaningful interpretation of the distribution of erosion without showing an overwhelming amount of variation. The 1 meter resolution can be too fine, producing very busy L factor outputs. And this can make it difficult to interpret where high versus low erosion estimates are occurring most predominantly in the landscape. While coarser resolutions lose fine scale variability and smooth the landscape too much to produce meaningful outputs. And so then finally, the slope cutoff variable for the grid accumulation method should be used especially at resolutions of 5 meters or better. And this helps to refine where in the landscape the greatest risk of erosion related to slope length is occurring by reducing the occurrence of false high L estimates on long slopes. However, once the landscape begins to lose its micro features at resolutions of 10 meters or greater, those statistical differences between using and not using the slope cutoff variable decreases. And so finally, this research is part of a larger study that also worked on comparing outputs from different slope angle calculations used in the S factor. Again, these outputs were compared across the same variation in resolutions for all sites.
Thank you, Amanda. Pushing it to the limit.
Yeah, I'm sorry.
No. All right, judges, feel free to unmute your microphones. Just also another little announcement before we do questions. We will have a small break after questions. So, you know, people can, either judges can write down scoring and such, so. I have a question. Can you talk about some of the skill sets or different areas of GIS that you had to learn in order to complete this project?
Absolutely. Before starting this project, I had absolutely zero programming experience.
Wow.
And it was such a huge component of being able to calculate that slope length for the L factor. And I took a class on it, and then I had to do some self-teaching on like the NumPy modules and converting the raster into an array to get it to actually calculate faster. So that was the biggest skill for me to learn, and I actually absolutely love programming now.
Oh, wow.
Been really excited to go further with that aspect of it.
That's great.
Yeah.
I have a quick question. Just what do you see happening next with some of this research you've done? What would you like to see happen from it?
Honestly, what I would like to see happening is more soil erosion estimates, like real world data being gathered. So this is estimating just the movement of soil, not just the soil that's reaching streams. So it's much harder and much more costly to gather that information. And the biggest hindrance between evaluating the effectiveness of the contributing area method versus the grid accumulation method is a real lack of real world data to compare these estimates to. But yeah, it's very costly to get, and I think that's a huge problem. So,
thank you.
Mm-hmm.
So going back to kind of your last slide about applying it to other areas, do you think your methods could be applied to a much larger landscape, like more of a statewide or a region-wide area, or are there, is the complexity of the landscapes make that difficult?
So I would say with the contributing area method, when you start using those much larger landscapes and much more complex landscapes, you start getting values that are so far outside of the RUSLE model and what it's been built to actually be able to accommodate. Because the RUSLE model was originally built using slope length as the factor of estimating erosion relating to length. So if you use the grid accumulation method, you get estimates that are more meaningful with how you interpret RUSLE outputs. So you can use that at large scale projects, so large area projects.
All right. Well, thank you, Amanda. If we don't have any more questions, we're going to take a 3-minute break. So about 3:51 is when we're going to start back up. So I will wait for everyone to appear to be back. But up next, we will be having Michael Mizer. So be ready to present, Michael. And see you guys in a couple minutes. All right, our 3 minutes are up. Do we have all our judges back? I do see all of the judges. Michael Mizer, are you ready in here to present?
Yep, I am.
Great. Let me introduce you real quick. Michael Mizer is from the University of Washington, Tacoma, and is presenting on green investment zoning, mapping opportunity in communities supporting retail cannabis operations. And also he has a second account in here that will be doing the presenting, and it's the Samuel account. So keep your eye on the chat, Michael. I'll be giving you the time indicators, and you have the floor now.
Thank you. This is going to be a little interactive for all you folks. It's because the PowerPoint presentation was on a 2x3 poster instead of a series of slides. So I'm going to post a link in the chat, and you're free to download that PDF. It works best if you set it to 100% and you use the hand pan button to move around while I discuss it. The link is in there right now. I will share my screen and discuss it while you pull that up per your interest. And here we go. So I wanted to address land use as it occurred by cannabis policy regulation that was set forth in 2017 or updated. When reviewed, the original blotter that suggested land that wasn't usable because it was in proximity or would be in proximity to a service that was grouped as a prohibition under the restriction of operations. You had a very diluted map, which made Tacoma seem, two things: either overly accessible to parks and services that would aid in youth development or transition into adulthood, or parks and recreation, or you had zero spaces where cannabis stores could legally operate. So I went down to block by block levels and analyzed, well, not totally analyzed, but pulled out detail that could be used for analysis to determine what facilities aren't available in proximity to these services that are discussed. Again, that's early childhood, young adult, and parks and recreation with cannabis retailers. The age groups that I looked at included 5 to 9 and 7 or 18 to 20, which there's a roster in the lower right-hand corner that gave a heat map of density, looking with very little difference around Tacoma as a region, but breaks down into density by block group as it occurred in a graph below with the data. The zones are dedicated in the larger map with the Voronoi polygons as a percentage of the excise tax that is earned at those locations. And that's a percentage of $151 million in Pierce County since 2015. There's data to the right of the map. I'll zoom in here to 100% so I can show you while I discuss. There's the stores and zones that they operate in, and the parcels that were analyzed as they occurred within 1,000 feet approach instead of a 1,000-foot boundary around the footprint of the perimeter. This opens up a few things. You can see in the south end of Tacoma, there would be a large conglomerate density of the focus group in these areas. And you can see by land use that there's evident room for early education, parks, recreation, or facilities around here, and a little bit down by Lakewood as well. Or in the contrary, you could look at the east end or north end of Tacoma and suggest that around areas around the UPS and the West End may be open for cannabis regulations or operations to maybe earn additional tax revenue in that region. And in scrolling through, and you identify these tables at the bottom, they break down occupancy by acreage of land use type, and it provides a useful graphic to identify which services or access to services might be induced in a lending plan for under the Community Reinvestment Act, 1977. And I looked at this for the very particular region that the use of cannabis as it occurs in adults is rather high. It's about 66 to 68% on any given survey that you would pull. And community reinvestment with this much excise tax could serve the way to open up tax-based incentives or abatements of tax based on improving the availability of these services in some of these impoverished regions. And that's all I have. Thanks.
Thank you, Michael. Opening the floor up for questions.
Hi, this is Heather. I just I wanted to make sure I heard correctly. Towards the end, you were mentioning, I think the percent of like the adult population that consumes marijuana being around 60%. Is that what I heard?
I would want to step back on that and say consume or approve of.
Oh, okay.
Probably a more accurate word to use in that situation.
Okay,
I
okay.
wouldn't say that in any given survey people would admit to 66% usership, but I wouldn't be too far from speculating that in any adult majority.
Okay, thank you. Thank you for that clarification.
Can you summarize again the charts you have in the lower right, kind of what those findings are showing?
These are statistical selections through ArcMap that once I had my paths identified through the network analysis, I isolated the top 10 and bottom 10 parcel types that are available by footprint acreage, with number 1 being at the bottom of the charts based by acreage. I haven't gotten to do any on the ground truthing analysis of the quality of these neighborhoods, but maybe you can tell by my character I might be a little familiar with where these activities locate, and I'm very familiar where the parks and early childhood development is because of my daughter. So it was interesting to me to see what wasn't available in these places as to what may be protected under land use as current use open space RCW 8433 seems to be protecting, if not, not using under some statute that protects it from development. It gave a really neat breakdown of what was available. And on the farther right, you have a summation of average values for land use and land values there by how they occurred in my selections.
So I have a question. The industry itself seems like it can benefit from site analysis like this more than maybe most other industries because it is so regulated.
Yes. Yes.
Have you found that there's either a lot of GIS type analysis going on or maybe a lot less?
Oh, absolutely zero. I think I found that I am a pioneer in this field, and I am maturing it to actually evaluate land for hemp farms in the Midwest following this after the summer. I don't know what work looks like, so it looks like I could probably mature this into developing analysis for cities greater than 300,000, cities that have unique geometry and geography about them, and other development in this industry. It's a goal of mine to see that hemp renewables is something that's input into future manufacturing, and we bring it to Mars with us. So yeah, there's a lot of work to be done in adjoining industries.
Right. That's very interesting. Thank you.
Was your analysis specifically focused on cities as the green area in Pierce County, that sort of unincorporated area? Was that taken into account in this, or was it specific to cities?
It was for cities that I could appeal to governance to make decisions around the policy of where things occur. So at the upper level echelon, it would have to go through the LCD in Washington State. I think they have enough on their plate of what they need to revise in policy and how it treats urban populations. So maybe these other municipalities and governments may listen to allegiances which they will enact. Statutes might operate or open up space for use. Again, this is taking away the idea that the 1,000-foot buffer gives anything more different than the 1,000-foot approach as terms of accessibility, because we have private land values, we have fence or private land laws, we have fences, we have inaccessible terrain outside of these normal pathways. So why would we take opportunity away in those surrounding areas by a generalization such as a 1,000-foot buffer?
I have a quick question. Does this analysis you've done or the research you've done, would that be a way to apply forecasting for future populations and developments that you could apply that to those forecasting efforts, or is this more of a snapshot?
I would definitely open up these. There are a number of proprietors in the industry for sales in which I would approach with plans to open up in some of these parcels. Does that answer your question? Yes, I would use this to forecast places to open establishments, either for the operation and sale of, or for services contrary to and more along the lines of well-being.
I was thinking more forecasting around other activities, you know, the education facilities, and just as the population outside this industry grows and changes and evolves, how can you apply that?
Where those things would be adequate as considered to where they are in lack of now. That's yes. Yeah, I think that's sufficient.
Thank you.
All right, that's our time for the questions. Thank you, Michael. We will move on to our final presentation, and we are going to be hearing from Megan LaFever, Anna Ledgerwood, and Stacia Wrench from the University of Washington GIS Certificate Program, and they will be talking about Whatcom County wildlife crossings. And I also wanted to take a second to mention that while we only did allow a maximum of 3 presenters based on tradition, that Peyton Morrison, who is also in attendance, contributed to the initial work of the project. So Megan, Anna, and Stacia, we're turning the floor over to you.
All right, hello everyone. Our project is Wildlife Crossing Site Selection in Whatcom County, and our group is made up of myself, Anna Ledgerwood, Peyton Morrison,
Megan LaFever, and Stacia Thompson-Wrench.
Tonight we'll be covering our project summary, background, objectives, research and methods, map analysis and results, ending with our conclusions.
For this project, we chose to focus on wildlife crossing site selections. According to a study by ARC Solutions in 2017, in a single year, wildlife vehicle collisions cause over $8 billion in personal expenses to the US population, 200 deaths, 26,000 injuries, and not to mention the damage to wildlife and habitat connectivity. Wildlife crossings are designed to help alleviate the physical and financial costs associated with wildlife vehicle collisions, connect fragmented habitats, and decrease mortality rates of the affected species. Our project's region is Whatcom County. This area encompasses both urban and natural areas, including Bellingham and the North Cascades National Park. Here we are focusing on areas in which there have been a high level of wildlife collisions and carcass removals along roadways. There are also many fish passage barriers in the region that are slated for reconstruction in the next 10 years that would be cost effective to modify into wildlife crossings.
We needed to compile traffic, wildlife, and terrain data to pinpoint problematic areas. Using spatial analysis, we determined optimal sites for wildlife crossings across existing roads and fish passage barriers. These barriers include culverts, dams, and other structures that impede the movement of fish along a stream. We helped our sponsors pinpoint hotspots with high wildlife vehicle collisions and carcass removal data points to locate sites that would be suitable for constructing a wildlife crossing. We then created a series of 24 maps incorporating fish passage barrier locations that are planned for correction in site selection. Finally, we wrote a report detailing our findings.
We reached out to professionals involved in existing wildlife crossing projects like I-90, Highway 97, Route 20, and the Oregon Department of Transportation for the backbone of our research to help us narrow down factors of importance. Many factors must be considered when selecting a site for a wildlife crossing, including construction complexity, topography, traffic data, existing structure replacement projects, land management, habitat connectivity, priority areas, protected wildlife species, and more. Some factors lend themselves to usable data, such as traffic data, collisions, and carcass data, while other factors are subjective, incomplete, or unavailable, like habitat connectivity and construction complexity, which can make data acquisition difficult or impossible. We ended up focusing on wildlife vehicle collisions, animal carcass removals, and known habitat areas as key components to our site selection. Carcass removal points are assumed to be unreported wildlife vehicle collisions, as we had to assume this due to the knowledge that not all wildlife vehicle collisions are reported, and use carcass removals to supplement the data. Our initial plan for our project's methodology was to compile relevant ecological and traffic data from state and local agencies, select the most important data sets, and create several weighted overlay models for site selection using those data sets. We designed and built a geodatabase containing over 40 data sets from Whatcom County, Washington State Department of Transportation, Washington State Department of Natural Resources, and more. We sifted through this massive database and selected the most relevant data, focusing on wildlife vehicle collisions, wildlife carcass removals, traffic, and habitat data. During our map creation, we found that most of our data was constrained to roadways, which we expected. This meant we were working with a linear network. What we didn't expect was that Esri software doesn't have a way to find patterns along a network. Pattern analysis in Esri software calculates distance across a Euclidean plane, or as the crow flies. Esri software has no way to run any kind of pattern analysis along a road network. Oh, hang on, go back. Most of our data is in vector form, which meant that if we wanted to run a weighted overlay model, we would have to change many of our layers into rasters. Rasters aren't ideal for linear networks and point data along those networks. Since raster data, display data has equally sized square cells across a plane, they don't display line fluidity well. Because of these two factors, we tossed out our original idea of running Esri's weighted overlay tool with rasters.
As Megan mentioned, our original plan to create weighted models incorporating various raster layers proved to be unusable for several reasons. We wanted to see what kinds of pattern analysis we could run on the wildlife incident data beyond what Esri currently offers. Our research led us to a toolset developed by a team of GIS specialists at the University of Tokyo called SANET, which stands for Spatial Analysis Along a Network. SANET has a kernel density estimation tool that was of particular interest to us since it calculates density of points along a network, not across a Euclidean plane. Another benefit of SANET is that its output files are in vector format rather than as a raster, which preserves line fluidity and accuracy. SANET is available to academic researchers on a case-by-case basis, and we were fortunate enough to be granted access to the software. The top map here shows the roads in Whatcom County, our area of focus. State highways and freeways are symbolized with a thick gray line, while local roads are symbolized with a thinner gray line to distinguish them. The bottom map shows wildlife incident points in Whatcom County, as well as sections of road that are disconnected from the larger road network, which are symbolized in pink. Many of these pink sections are Forest Service roads or sections of road that run through Skagit County to the south or British Columbia, Canada to the north. SANET's tools require a connected network, so these pink sections were not included in our analysis. However, as you can see, the majority of wildlife incident points, which are symbolized in dark red, occur along connected roads within the network. Using SANET's kernel density estimation tool, we developed two models to find wildlife crossing sites in the county. One, the human safety model, finds the areas of highest wildlife incident point density to highlight the most dangerous areas for wildlife and humans. The other, the elk priority model, focuses on elk incidents to highlight the areas that are most dangerous to this threatened species. With these models, we found 6 possible wildlife crossing sites and chose 2 of these as our proposed sites due to their proximity to a fish passage barrier. This map shows the results of our SANET kernel density estimation analysis, which looked at all wildlife incidents along the connected road network. Point density is classified into 5 classes, with the highest and second highest value classes symbolized in red and orange respectively. The red areas are the most dangerous areas for humans and animals according to our analysis. 4 out of the 6 highest danger areas are near the city of Bellingham on the bottom left of the map. This map is a large-scale view of that area we were just looking at around the city of Bellingham. You can see the 4 red highest danger areas, as well as fish passage barriers slated for future correction that are nearby, which are symbolized as hollow diamonds. We chose the fish passage barrier that is symbolized in yellow on the map as the first of our 2 proposed crossing sites. And here is an even larger scale view of that selected fish passage barrier, again symbolized in yellow. We included small streams in blue, sensitive aquatic areas near roads in light purple, and LiDAR in the base map to show ground cover. Each fish passage barrier blocks or partially blocks a stream. The barrier we have chosen, number 994233, impedes stream flow underneath Interstate 5. It is not only close to one of the highest danger areas in red, but directly overlaps an area of high danger in orange. We also created a series of 4 comparison maps for each of our 2 models, resulting in a total of 8. We compared our SANET kernel density estimation results against annual average daily traffic volume, against speed limit, and against 2 rankings developed by the Habitat Connectivity Investment Priorities Project at WashDOT. These rankings are safety, meaning the danger to animals and vehicles, and ecological vulnerability, meaning danger to threatened species such as elk.
We wanted to provide views of both overall wildlife incident density and of the incident density of a threatened and ecologically vulnerable species. For this reason, we also ran an analysis of elk incidents using wildlife vehicle collision and carcass removal data in Whatcom County, using the same SANET kernel density estimation tool. The following maps will focus on our elk priority model. The same band size and cell size parameters were used in this second analysis. The top map displays the elk incidents recorded by state and local agencies. The area in green to the east of State Route 9 is an elk winter habitat area. The bottom map displays the results of the SANET kernel density estimation, using a band size of 1,000 and a cell size of 100. Only one area of highest elk incident density emerged from this analysis, which is symbolized as a thick red line. This result therefore focused our wildlife crossing selection to this section of State Route 9. This map shows this section of State Route 9 at a larger scale, with 4 nearby fish passage barriers slated for correction symbolized as hollow diamonds in the elk winter habitat area, again symbolized in green for reference. We have chosen the fish passage barrier to the south of the area of highest elk incident density as the location of our second proposed wildlife crossing. We chose this fish passage barrier location for its proximity to the area of highest elk incident density and its proximity to the elk winter habitat area. And the proposed elk wildlife crossing is 991106. We have also created a similar series of comparison maps for the elk incident density analysis as we did for our all species wildlife incident density analysis. The following 4 maps include a comparison of the elk incident density data against annual average daily traffic volume, speed limit, in 2 rankings developed by the Habitat Connectivity Investment Priorities Project at WashDOT. These rankings are safety and ecological vulnerability.
This project produced a geodatabase with over 50 datasets, 24 maps, and a report explaining our findings. Our analysis led to 2 wildlife crossing sites being chosen, based on 2 separate models focusing on overall danger and ecological vulnerability. Our next step is to submit our proposal to our sponsors at Whatcom County and Washington State Department of Transportation. We are optimistic that the construction of these wildlife crossings will greatly benefit drivers, passengers, and wildlife in Whatcom County.
We would like to say thank you to all of the folks who made this project possible from its start back in October of 2019. Thank you to Dr. Atsu Okabe and his team at SANET at the University of Tokyo, to Terry Johnson, Robert Waddell, and Keith Folkerts at the Washington Department of Fish and Wildlife, which graciously allowed us to use their elk habitat data. And then our primary sponsors, Chris Elder at Whatcom County, Kelly McAllister, Mark Hirschfield, and Glenn Callis at WashDOT. Thank you. Any questions? I see one in the comments here from Amanda. Do you know why SANET is currently only for a case-by-case use? Well, the people who developed the software, so this GIS team at the University of Tokyo, they wanted to make sure that their tools were only to be used by academic researchers, so they didn't want corporations or government organizations to use this. They really intend this as for academic use only, since it's a free software that they make available. Hopefully Esri will incorporate network pattern analysis tools into future versions of ArcMap and ArcPro. But until then, it looks like SANET and their tools are really all that's available.
I'll be checking on that.
Yeah, take note, Heather.
I was going to ask on that note if you guys contacted Esri and had a conversation about that with the limitations.
Yeah. We have not. We did some digging into the Esri forums and saw similar questions by folks looking to run similar analyses along networks, looking for patterns. And the response by Esri employees was that, unfortunately, it's not a capability in their current software, but that perhaps in some future version of ArcPro, they might include it. So it would definitely be an interesting conversation to have. We'd love to talk to Esri and see if they would be interested in maybe incorporating some of the SANET tools.
Yeah, I'm just curious if that's one of those things where it was available in ArcMap, but not in ArcPro yet.
I'm sorry?
I think 2 of us were talking at the same time. I was just curious if it's one of those cases where it's available in ArcMap still, but not in ArcPro yet.
Unfortunately, it's available in neither right now. So even Pro hasn't adopted any of these network pattern analysis tools. The SANET toolset is really useful because it can actually run independently of Esri software. So all you need are the individual layers. So your network layer and then your point layer, and then it does the analysis completely separately, gives you an output file, which you can then bring into any software you'd like to use. So you can even use this with open source software such as QGIS as well.
Good question.
How did you run across the SANET tool set?
So we were looking for similar projects that wanted to find patterns along a network. There was a study run by a team of researchers in Spain looking at traffic accidents in the city of Barcelona. And they listed the SANET tools as their major analysis tools. And so we went to the SANET website, looked at what they offer, and then sent an email to the director, Dr. Okabe, and he was generous enough to allow us to use it.
Yes.
Did you discover any issues in your modeling? I noticed in, I think it was the human safety model, you know, there was a lot of
Yes.
in downtown, and then up in Mount Baker area, there was kind of some bats up there. Was that an outlier of the analysis, or were those still a valid
Right.
location?
So those were errors in our analysis. And actually, Stacia, if you could go back to that slide, we can show you. Let's see here. I'll tell you when to stop. So this map, yes. So you can see there's an area of State Route 542 up by Mount Baker where there are, they're kind of blended into one at this scale, but there are these two areas of highest animal incident density that did appear as errors in our analysis. We went back and looked at the point layer to see how many incidents actually were in that area, and there are only two, and they're actually quite far from what the analysis said should be an area of high density. So we interpreted those as errors within the analysis. We know that the SANET tools, they specify that it needs to run within an interconnected network. And this area of State Route 542 ends in a dead end at Artist Point. So we hypothesized that because of this dead end, that may have interfered with some of the algorithms within the software.
I have a strange question, but carcass removal data, I've never seen that before. Where did you guys get that from? Whatcom County?
So we got that from our contacts at the Department of Transportation. We were in touch with Kelly McAllister, who works extensively on wildlife safety along roads. He's been a part of many state wildlife crossing projects in the past. And he said that typically what he and his teams advise people to use is not only the collisions data, but the carcass removal data, because what they've found is that most people don't report a collision with an animal, and that typically is just left as a carcass. So the only way that that event is recorded is as a carcass removal. So he suggested that we actually supplement the collision data with the carcass data because it gives a fuller picture of events on roads.
I also want to add in there that they originally only gave us state road data on carcass removals, and we later got in touch with Glenn Calitz, and he was able to compile all of the local road collisions and carcass removals from there, and we were able to do a more in-depth all of Whatcom County roads.
Mm-hmm.
I'm sorry, I may have missed this. Was speed a factor, traffic speed a factor of your analysis for site suitability?
So it wasn't necessarily a factor that we included in our site selection, but we did run a comparison looking at speed limit along sections of state roads. So in this slide, you can see that the top right map looks at speed limit compared to those areas of highest animal incident density. And you can see that of those four highest danger areas in red, they correspond to mid-level or mid-range speed limits, so typically between 50 and 60 miles per hour. There is one that kind of bridges an area of mid-range speed and high speed limits up in the north. So we included these comparison maps for people to look at possible variables that might be affecting these high danger areas, but we didn't include it necessarily in our site selection.
Yeah, the main reason we put it in there was also because in some of our research, it said that animals would cross more in like the mid-range speeds instead of low. They could cross easily but not get hurt, and high, they would see too many obstacles and not want to cross. So the mid-range speeds are kind of those, like, they're more likely to cross and they're more likely to get hit. So we just wanted to put that in there.
Perfect, thank you. And then in your collision data that you have, I'm assuming that's coming from WASDOT. Were you using the factors of were they fatal collisions or injury class collisions, or did you treat all collisions the same?
We treated all collisions the same for the purposes of this model. Of course, it would be possible to kind of just select for collisions that resulted in serious injuries or deaths. But we wanted to have as broad a data set as possible because we know that collisions are underreported. this data set is usually pretty limited. So when we actually compared the carcass removal data to the collision data, we had, I think, almost 3 times the number of carcass removals as there were collisions. So we wanted to have as broad a data set as possible. But of course, it's, you know, for future analysis, it would be useful to look at specific parameters like injuries and deaths.
Thank you.
On that note, I want to also add in that we used all sorts of animal carcasses, not just any deer or elk or any other ungulates. There were rabbits in there and gulls and owls. So there were things that, of course, if people hit a rabbit, they're not going to report it, but we still want to record it as this is an area of a wildlife incident where they're getting run over.
Mm-hmm. That could point to an area where lots of different species are using as a point of crossing.
Great, thank you. That is all the time we have for questions on that project. Thank you, guys.
Thank you.
And that's going to wrap up our presentations for the 2020 Dick Thomas Award and competition. We, Dan and I and the entire committee and conference volunteers, we want to thank everyone who participated, whether you're judges or students or volunteers. It was definitely a curveball, this pandemic and the cancellation of the conference, but all of your guys' patience, it's really appreciated, and your flexibility. So I can speak for myself. I'm very impressed with what I saw today from all of the competitors, and all of you should be proud. So, but I want to say, you know, a special thanks to individuals. Anna Yost was our, she was our coordinator, spiritual guide. The words are failing me right now. She was, she was in a, help me out, Dan. What's the word that I'm looking for?
Cattle prod? That's what she was doing. No.
She was in an advisory role. Thank
Yes.
you. And we are immensely grateful for her input.
Definitely.
Yeah. We know that Steve Beinborn is here. He's the president of the board for YURISA, and we are grateful for his oversight and his influence. And then a couple of people who helped with a lot of communications and grammar and editing. That would be Maddie Wheeler and Christina Shelf, who's also a judge, and Maria Sevier. We are very grateful for all of your input. It was not necessary, but you guys were there to help us with that. And Kirsty Burt obviously was our the conference coordinator and was definitely the overseer of our entire operation and helped us move this platform onto a digital platform. And so thank you very much, Kirsty. And I'm missing Josh Greenberg and Jason Eklund for all of the technical services that they provided for this, as well as Tammy Faulkner, who provided some oversight and also the financial aspects of the competition. Also, a side note to our advisors, Harvey Arnone and Bob Hickey and Matt Kelly, who were the advisors of the students. Thank you for you know, teaching your students and having them come up with amazing projects. And last, I want to thank our judges, because I know I put them through the ringer time-wise through the presentation. It is very hard to manage the time in this format, but I know you guys had quick turnarounds on judging, but thank you very much. And thank you for being patient with us as we tried to come up with the format for the competition. So other than that, we will, the judges will be sending in the results of their scoring to us later today. And the rest of you will be hearing about the results of the competition on Monday. I will be sure to send out an email on Monday morning. That way there's a little bit of, you know, anticipation and surprise for over the weekend. So thank you again for everyone who participated, and feel free to contact us with any questions that you may have. And thanks again.
Yes, thank you.
Thanks, everyone.
Great job, everybody.
Yeah.
Nice job. Thank you.
Everyone.